Hi everyone, welcome to another lecture, Physics 2. We are going to be talking about alternating current circuits. So in this chapter, we're going to be hitting the first 6 sections. And in this lecture, I will do sections 1 through 3. So we're going to start off with the motivation of why we should learn about alternating circuits, how we should analyze them, and we're going to talk about a really cool device called a transformer that you use every day. So let's get started. Why do we need to know about this? Well, most circuits use alternating current. So we're going to learn how to manipulate and use alternating current. Most of the power on our planet is transmitted from one place to another in the form of alternating current. So power and electricity is generated at a power plant or the Hoover Dam or a wind farm. And that power, the way it's generated as AC current. And we hook it up to some power lines, and that AC current flows down the power lines and goes to a transformer station, a substation. You probably have seen them, chain link fence around it, right, with barbed wire. And then from there, it goes to your house, all in AC current. And we're going to take a look at how this current is transformed into different voltages and even into DC in order for us to use it more safely and effectively. So to do that, we need a tool called a transformer, which uses the property of mutual inductance. So we'll talk about that. And so let's kind of get into what these objects are, this transformer. Well, you know that when you plug in your phone, you have this little piece attached to the end of your plug that is kind of like the go-between between the phone and the wall, right? And so what does that thing do? Well, what it does is it's a transformer, and it uses a property called mutual inductance to take the high voltage in the building, for example, in your home or in your building, ISA, you are running on 120 volts. And, well, your phone does not run on 120 volts. So we actually need to step down that voltage to around 5 volts or less in order to charge your phone. And that's what that brick does. That's what that little box does. I call it a brick because if you play video games on a console, or if you've, hung a TV, you've probably seen an extremely heavy and large box attached to your plug, your power plug. And you're going to learn very quickly why that thing is so heavy. So the second thing we're going to look at in this chapter, and we'll talk about this in the next video, is what an LRC circuit is, okay? And how an LRC circuit helps us tune into a radio station or change the channels on our TV. So just to wrap up this introductory section, right, we are going to use the same principles of electromagnetic induction that we learned in chapter 20, but we're going to talk about them in the context of some circuit elements and devices, okay? And then we're going to learn about the types of circuits that we power using AC voltage. So we need to develop some mathematical tools that will help us analyze AC circuits, because the way we analyze AC circuits is different than DC. So first, let's dissect the voltage source that we're going to be using. It's an AC voltage source, and it's created by the AC generator that we learned about at the end of the last chapter. So we know that in regular circuits from chapter 18 that we get a current whenever we apply a voltage, right? So the same is true for alternating circuits, except now our voltage is flip-flopping between positive and negative values, and so therefore our current is going to flip-flop between moving clockwise and counterclockwise. So if we take a look at the AC generator from chapter 20, we saw that the EMF generated by the AC generator varies with a sine function, right? And its magnitude was WNAB. That's what I like to call it, omega NAB. It's a voltage, right? This is a voltage, units of volts, and WNAB or omega NAB has units of volts. So what we're going to do is, because we're going to be using this a lot, we're going to rewrite that in terms of V, voltage. And so the amplitude of the voltage coming out of our AC generator is going to be V naught, which is equal to omega NAB. Okay, and then we're going to assume that we always start at 0. So the phi symbol in the sine function is going to be 0. We're just going to kind of like, we don't need to worry about it. And so that's going to turn the voltage coming out of the power supply into this function V naught sine omega t. And right, so we're going to be dealing with graphs of trig functions. So let's take a look at some of them, because we're going to be using these trig functions to interpret our current and voltage and charge in our circuit, okay? And these are going to have the same principles as in simple harmonic motion, which you learned back in chapter 12. We're using the same math here in AC circuits, but we're just looking at a different situation. So let's take a look at this sine function here, right? Sine of 0 is 0, so a sine function should always start at the origin, and the peak of the sine function is going to be a value of V naught, okay? And when it's down here, it's negative V naught. And the period of the sine function will be the peak-to-peak distance. It could also be the trough-to-trough distance. And it can be the 0 to 0 distance, but you need to be careful that you're choosing the decreasing or the increasing 0, right? You don't want to go from this 0 to this 0 because that's half of a wavelength. So the period can be written in terms of the frequency, which can be written in terms of the angular frequency, right? This is all the same stuff from chapter 12. And so we call this the angular frequency, and then we call F just the regular frequency. So in the US, well, in North America, pretty much, maybe not Mexico, the frequency that we choose to oscillate our electric power is 60 hertz. So if the frequency that we oscillate our voltage coming, from our house is 60 hertz, then the period would be 1 over 60, which would be 17 milliseconds. And then the angular frequency would be 2 pi times F, which would be 3.8 times 10 to the 2 radians per second, or 380 radians per second. Okay, so that's just kind of like an example here, a math example. So this is all kind of, should seem familiar to you, except now instead of talking about like a mass on a spring oscillating about its equilibrium position, we're talking about a voltage oscillating as a function of time. So the power, right? Let's talk about power, because power is important. Power is the rate of energy transfer, right? And essentially when we are sending electricity from one place to another, we're sending power from one place to another, right? We're sending energy from one place to another. So to look at the power that is transmitted by a voltage source, or maybe the power that's absorbed by a resistor as a function of time, what we're going to do is we're going to replace the V with V naught sine omega t. Okay, so we'll replace this V with V naught sine omega t to get the AC current version of power. So the instantaneous power, so that's the power at any time t, is going to be simply that direct substitution. So we're going to get V naught squared sine squared omega t divided by r, of course. And what you see is that the instantaneous power, or the power at any time t, it's going to oscillate between 0 and a max of V naught squared over r, right? Because sine squared only returns positive values. But this instantaneous power equation is not, the most like widely used, because our electricity oscillates so quickly, 60 hertz. We don't really care what the power is at, 0.1 millisecond versus 0.2 milliseconds, right? We're going to care instead about the average power. So let's look at the average power. And to calculate that, we're going to use a special average, okay? That's because if you were to average a regular sine function, right? Here's a sine function. It has just as much of its function is above 0 as it is below 0. So the average of that function would actually be 0, which is not super helpful, is it? So I meant to Google who came up with this root mean square idea. Somebody came up with this excellent idea to avoid that, to avoid getting this unhelpful 0 when averaging a sine or a cosine function. And this method is called the root mean square, and you're going to see it, I'm sure, in other classes. Okay, physics is not the only place where you will see a root mean square average. It happens in biology, it happens in statistics all the time. Okay, it's a common type of average, but here I can illustrate to you why we're using it, right? Because if we were to average a sine function, we would get 0. Okay, that would not be very helpful. So instead what we do is we do a root mean square average. And what we do is you square the function, take the average, and then square root it back to get it back to the original units. So that's the root mean square average. So it looks like this, right? So V root mean square is the square of that time-dependent function, then take the average, and then square root. And what you end up getting is the original amplitude of that sine function divided by square root of 2. So that's what you end up getting. So this is how you can relate the root mean square average to the amplitude of the sine function, which is V naught. Okay, it's just related by square root of 2. So the root mean square value, VRMS, guess what? That's actually the value that we write our user manuals for our electronic devices in, okay? Or if an electrician comes to your house and says, hey, you have 120 volts coming out of your wall, that value that he's actually telling you is the root mean square value. So that's why it's important to know this. This is the value that, is written on the fuse box. This is the value that is in all of the user manuals of your electronic devices, okay? Root mean square value. So if we wanted to take that root mean square value and figure out what would the voltage amplitude be if we were to look at it on a sine function, well, then we would take that VRMS and multiply it by square root of 2, right, to undo this, right, and to solve for V naught. And so what we see is that in our house, the V naught value would actually be 170 volts. So we're now going to, right, this was all to express the average power. So now let's express the average power. The average power, which is V naught squared over 2 from our previous sections, is going to turn into VRMS over R. Okay? So here's all the different ways that you can write average power. And you can write it in terms of V naught or VRMS. So the average power is replacing the V by VRMS. So let's do this example. If you've traveled a lot, or maybe you have come to the US from another country, you probably realize that any electronic device that you bring from another country may not work here, right? And vice versa. Anything made in the US may not work when plugged into the wall in another country. We're going to kind of dive into that and see what happens. So let's say you have a hairdryer made in the USA, and the RMS wall voltage here is 120 volts. This hairdryer is rated to only accept a maximum of 1.5 kilowatts of power. If more power goes into that hairdryer, it could blow up, basically. So what we're going to do is we're going to find the power consumed by the hairdryer if we connect it directly to a wall outlet in Australia. Will the hairdryer blow up? The amplitude of the voltage in Australia is 325. So we need to treat the resistance of the hairdryer as the same regardless of the wall voltage. So let's write down what we were given. So we were told that in the USA, the voltage here is 120 volts and the hairdryer can only accept, as much as 1500 watts of power. And the question is, how much power is consumed by the hairdryer in Australia, where the V naught value is 325 volts, right? And I'm using V naught because take a look what it said. It said voltage amplitude, right? Voltage amplitude is V naught. RMS is VRMS, okay? So let's say we want to find the power. What is the power in Australia? Well, using the V naught value, we get 1/2 V naught squared over R, right? I'm simply using this guy right here. So, but I don't have the resistance, do I? So I can't, if I don't have the resistance, I know this, there's no way I can figure out P. So I might need to use this information up here to find R and then plug that in. Do you see that? So let's go ahead and do that. So in the US, the resistance of the hairdryer we can figure out. So the power is 1500, and then using VRMS is 120 squared over R. Now I can solve for R as 120 squared over 1500. Which is 9.6 ohms. So now I have R. So now I can figure out how much power is consumed in Australia. So V naught is 325 and the resistance was 9.6. So how much power is that hairdryer taking in? It's taking in, a whopping 5,501 watts. So that's, well over 2 times the rated power of your hairdryer. So that's not great, right? That's not going to be very good for your hairdryer. It could be sending in too much current and start to melt things, and it could even catch on fire. So although you might find a power adapter at Walmart that would fit into a socket in Australia, it may not be a good idea to actually do that because of how high their voltage is there. Okay? So I thought that's kind of a fun, right? It's kind of a fun example, right? So sure, get all the adapters you want, but you need to look at your electronic devices carefully to make sure that you're not going to blow it up. Okay? So, so now we're looking at, in this slide, we see that the average voltage could be 0, but the average power is not 0. And so why is that? Remember, the average voltage is 0 if we average it like the old-fashioned way. The average voltage is 0 because we have just as much sine function above 0. Here, that's not above 0. This is above 0. Just as much sine function above 0 as we do below 0, right? So that would average to 0. But sine squared is always above the 0 line. So sine squared is always above the 0 line, and therefore its average is 1/2. Okay? So just a fun fact there. This problem is, it's a little tricky, at least the way that I demonstrate it might be a little bit tricky, okay? I'm demonstrating it mathematically. So if you want to do it like a quick way, you have to be really good with the unit circle, okay, from geometry and trig. So let's dive in. So we have a resistor and it's connected to an AC voltage source, okay, described by equation 21.1, which is this, okay? And the question is, at which of the following times, t equals 0, t equals 1/8 of the period, or t equals 1/4 of the period, at which of these times is the instantaneous power equal to the average power? So to mathematically solve this, so here's the answer, obviously. So how do we get this answer? Well, so to solve this, we need to equate the instantaneous power to the average power. Okay, and we're going to use V naught because I have, we just, it doesn't matter, right? You can use V naught or you can use VRMS, but they have to match, right? So you would have to express this properly in terms of VRMS, and then you can match it to this. But let's just stick with V naught so we have less work to do. So we're going to equate this to this, right? At what time are those two equal? So let's set it up. So V naught squared times sine squared over R. When is that going to equal 1/2 V naught squared over R? So mathematically, we can find this, right? Some stuff is going to disappear, cancel out. For example, the R's and the V naught squares. Okay, so what we're left with is what we're essentially asking is at what t does sine squared omega t equal 1/2? So how do we solve that? Well, you take the square root of both sides, okay? Take the square root of both sides, and then you're solving when does sine omega t equal 1 over square root of 2? Well, you might recognize 1 over square root of 2 as square root of 2 over 2, right? It's just the other way to write it. So then if you see square root of 2 over 2, you might further recognize, oh, that sounds strangely familiar from my days in pre-calc or pre-algebra or whatever class. That is when theta is at 45 degrees or pi over 4. And so then you would know that this stuff in the middle, omega t, equals pi over 4. Okay? Let's say you didn't remember that. What would you do? That's where this comes in. Let's say you didn't remember that and you're back at this, you're back here at this stage. Well, how would you solve this equation mathematically? You'd take the inverse sine of both sides. You would need to make sure you're in radian mode, okay? Because this inside here is in radians. And so then you would figure out that, okay, when you take the sine of both sides, you get omega t on the left and you get 0.785 on the right-hand side. Okay? And so we need to figure out how much of a period is 0.785 radians. Well, I know one full period is 2 pi radians. Okay? So if I divide 0.785 by 2 pi, then I can figure out how much of my period I'm in. Okay? So 0.785 radians, and I'm basically converting that to periods. I'm going to divide by 2 pi radians. My radian units are going to cancel. And I'm doing 0.785 divided by 2 pi, which gives me 0.1249. I'm going to recognize 0.1249 is roughly 0.125, which is 1/8. And so therefore, my answer is 1/8 of a period. Okay? So the other way, if we go back and let's say you're recognizing some common values on your unit circle, all right, you're going to get omega t equals pi over 4, and you're going to do the same conversion factor. How many periods is in pi over 4? Well, that math comes out to be a little more exact. You get your 1/8 right out of it, right? Because you do pi over 4 divided by 2 pi. That's 1/8. Okay, so this is kind of like the two separate ways to solve this, right? Using the mathematical way. There's a graphical way that you could solve it. So I'm going to use this. This is not the greatest graph of it because of how this graph is divided. Okay. But what you're matching up is you're saying, okay, when is this sine function, sine squared, equal to 1/2, right? So sine squared is the red squiggly line. And 1/2 is, so if this is an amplitude of 0 to 1, then 1/2 would be right here. And so then you're looking for where does it cross, right? It crosses right here, and it crosses right here. One period is all the way over here. So you're going to look at everywhere it crosses, and you would use these X crossings to figure out how much of the period it is. But you can see this is divided up by 5s, 1/5, 2/5, 3/5, 4/5, 5/5. So this is not the greatest graph to do that because it's in fifths. All right. And you're not going to get an exact value because you're somewhere off of that grid line. So it would not be easy. But if you had a graph of a sine function that was in fourths, you would be in business. Okay. So, so the answer here would be 1/8. Okay. There's also more spots. But it's not this one or this one. But it also happens in other areas, as you can see clearly here, right? But 1/4 was not one of those areas, and 0 was not one of those areas. So it happens at t/8 and some other spots too. Okay. So, so that was that got the concept, kind of long for a conceptual question. Let's wrap up this section. So we are basically looking at the math that helps us describe sinusoidal functions, okay? And we characterize AC voltages as sinusoidal functions. We have to do a fancy type of averaging in order to interpret the power of a sinusoidal varying voltage. And now we're going to look at transformers. I always say that in my head. Can't believe I said it out loud. So why do we need to know about transformers? Transformers are important because in power lines, we actually run the power lines at super duper high voltages, like hundreds of thousands of volts. And transformers allow us to change the amplitude of that voltage to something way more manageable for our home and safer for our home. And those bricks that we talked about that are at the end of your PlayStation or your cell phone or your laptop, those all have transformers on them too, right? Because these are sensitive devices and we can't just go sticking 120 volts into them, right? We need to kind of tone it down a little bit. So that's why we need to know about transformers. So in this kind of slide, this is kind of motivational. It's kind of like, it illustrates the importance of knowledge of this, of transformers. And I'm not going to go in too much, but the reason why power lines are operated at such a high voltage, hundreds of thousands of volts, is because we want to maximize the power while minimizing the current, okay? So we want a lot of power, which means we want a lot of energy transfer from one place to another, but we don't want a lot of current in there because when there's a lot of current running through stuff, it gets hot, right? And we start to lose heat and thus lose energy. So to minimize energy loss and to maximize power transfer, we operate at very high voltages. These voltages that we're talking about of more than 100,000 volts, this is going to be the voltage between adjacent cables, okay? And that's because, what do you mean adjacent cables, right? If you kind of look at this picture, there's a pair of cables everywhere, right? There's little pairs. Why is there a pair? Well, because you need a complete circuit, right? We can't just have one cable coming from the power plant to our house, right? We need a complete circuit in order for current to flow. So we have to send a cable back to the power plant to complete the circuit. And that's exactly why there's two cables. So when we talk about 100,000 volts, we're talking about the voltage between adjacent cables, and we're not talking about the voltage from end to end, okay? So we're not going to do any problems where you would need to differentiate that. That's just kind of a fun fact. So I mentioned this already a couple of times, right? The voltage in your home cannot be super high because it's dangerous. There's a risk of being shocked. The higher the voltage, the more amps you can encourage, right? The more charge you encourage to flow through the voltage. And so if we have really high voltages, we can encourage a really high current, and we don't want to come into contact with really high current because we would get burned or shocked or go into a ventricular fibrillation. You guys probably can pronounce that word way better than me, right? So in order to reduce the risk of accidents, we must step down that voltage of roughly 100,000 in the power lines to 100 or so. Transformers are how we do that. So a transformer is a device that can raise or lower an AC voltage to a desired value, okay? And here's a transformer right here. So a transformer, now here's the answer to the question, why are those bricks called bricks? Well, because they're very heavy, right? What is the heavy part? The heavy part is this iron core that makes up most of the transformer. And it's iron because iron is magnetic, and I'll explain why we need it to be magnetic. On each side of this core, we have coils of wire. On the left, we have the primary coil, where we input the voltage that we want to change. And on the right-hand side, we have the secondary coil, which what comes out is the new voltage that we want. So how is the output voltage produced, right? What we're doing is we're hooking up something to the primary coil. What is creating a voltage out of the secondary coil? Well, you actually already know the answer to this question. It's called induction, right? So when you apply an AC voltage to the primary coil, you're applying a current that varies with time. And that current is going to produce a magnetic field this direction. Well, it's going to produce it in also varying directions, right? Because this current is changing, it's alternating between left and right. So we're just taking a snapshot and we're just looking at the moment that the current is pointing to the right. And so if you use the right hand rule by putting your thumb of your right hand in the direction of this current, and then your fingers are going to curl inwards, and you're going to see that the B field is pointing up and it's changing, right? So we have a time varying flux being induced in this coil. And so here's where the magnetic core comes in. What this core does is it acts like a channel, and it channels the magnetic field like this so that it goes straight down into this coil, okay? And when that magnetic field is changing and going down into this coil, it's producing a current, right? Because we have a changing flux. And so the current that's produced on this coil is actually an induced current. And it's going to have a smaller voltage amplitude or a larger voltage amplitude. And whether it's smaller or bigger depends on the number of coils in each coil. So let's take a look at that, right? The amplitude, if the number of coils is different, then the amplitudes of those two are not equal. So we can take a look at the flux generated by the input voltage. Okay, the input voltage is going to equal the number of turns times the change in flux with respect to time. The output voltage is also going to equal the number of turns, but the number of turns of the secondary coil times that very same magnetic flux. And so since these two are equal to each other, we can substitute. And when we do that, we find that the ratio of the output to input voltage is equal to the ratio of the number of turns of the secondary coil to the primary, okay? So this ratio is true regardless if we're talking about the time-dependent voltage or the amplitude or the VRMS. So this equation is the transformer equation, and it basically tells us how we can transform one voltage value into another by the number of windings on the primary coil and the secondary coil. Okay? So, in other words, let's take a look at those two cases. In a step-up transformer, we need N of the secondary coil to be greater than N of the primary coil in order to get an output voltage that is greater than the input. So let's take a look here. What I've done is I've solved for the output voltage, right? The secondary voltage. In order for this value to be larger than VP, we need this number to be greater than 1, right? Which means that the numerator is greater than the denominator, or NS is greater than NP, right? So we call that a step-up transformer. So the number of coils on this side is greater than this side in a step-up. In a step-down transformer, we need VS to be smaller than VP. So if I set up that equation again, if I want VS to be small, then I need this guy to be less than 1, which means that NP is greater than NS, right? The denominator must be bigger in order for NS over NP to be less than 1. So that is a step-down transformer, and the output voltage will be smaller than the input voltage. So if we assume that no energy is lost during this transformation, then we can kind of take a look at the following graphs here. So the top part of this graph is the input voltage, okay? And I wrote input there just to be clear. It's the input voltage and the input current, okay? And in a step-up transformer, the output voltage increases, right? So we have a larger amplitude now. But what happens to the current? The current actually shrinks. Opposite case for step-down transformer, right? The voltage decreases, but the current increases. And why is that? Because if we don't lose any energy during the transformation, the power delivered must remain constant, okay? If no energy is lost, then the rate of energy delivery is going to be constant for the input and the output. And so if we're stepping up, if voltage is increasing, then in order to keep power constant, the current must decrease, right? And if we're stepping down, in order to keep the power constant, if the voltage is decreasing, well, then the current must increase to account for that, to keep P constant, okay? It's kind of like here, as you can see that a little bit better. So when you solve for current here, right, this is setting the powers equal. The power transferred from the primary coil to the secondary coil equals the power transferred into the secondary coil. If you keep those powers constant, you can see why if one goes up, this one must go down. We can also see that the current relationship and how it's opposite to the voltage. So if we solve for current, okay, and we develop the ratio of the currents, you can see I color-coded the primary and the secondary, and you can see that the relationship between the ratio of the secondary current to the ratio of the primary current is inverse to the number of coils. And whereas in the voltage ratio, it's proportional, right? So that is because the power must remain constant. So let's do an example. Let's say, okay, we're analyzing the Hoover Dam, all right, which is a hydroelectric power plant. And this power plant can generate 133 megawatts of average power, okay? This 133 megawatts of power is delivered with a 8 kilovolt RMS voltage to a transformer and that is connected to a power line. And that power line operates at 5 times 10 to the 2 kilovolts. The question is, what is the ratio of the number of windings in the secondary coil of the transformer to the number in the primary coil? So in other words, what is NS over NP? Part B, what is the RMS current? So let's find out the ratio of NS over NP. Well, we know that this power must remain constant, right? The average power, 133 megawatts, which is 133 times 10 to the 6 watts. And we know that the input voltage is 8 kilovolts, which is 8,000 volts. That's the input. And what we need is we need it to go up to a really high voltage for the power lines, right? Because we already saw that we need really high voltage in power lines. So we need to step it up to 500,000 volts, which is 5 times 10 to the 2 kilovolts. Okay, so just be wary of that. It's a very strange way to write that. They should just write 500 kilovolts, but whatever. So here's our transformer. And so what we want to do is we want to find the ratio of the windings. So, well, we know how the voltage ratios are related to the windings. So that's through this equation right here. So I want to solve for NS over NP. I'm going to rearrange this equation to solve for NS over NP, which is going to give me VS over VP, the output voltage divided by the input voltage. So output voltage, big number, divided by input voltage, the small number, because this is a step-up transformer, and that ratio ends up being 62.5. The question for part B is, what is the current running through that high voltage transmission line? Okay, so we know the power through that line, we know the voltage of that line, so we can certainly find the current through that line. And if we use all RMS values, then we need to use P RMS. So the power then is going to equal 133 megawatts. Our VRMS is 500,000 volts. And we can solve for IRMS, which is 266 amps. Pretty straightforward, right? Keeping track of what's the input and what's the output, might be the most difficult part here. So So let's look at this conceptual question, and then we'll wrap up this lecture. If we have a certain step-up transformer with 100 windings in its primary coil and 250 windings in its secondary coil, if we reverse the connections so that the primary becomes the secondary and vice versa, sending 120 volts RMS into the reverse transformer, what will be the output? Okay, so there's a lot going on. So we'll draw our transformer, 100 for the primary, 250 for the secondary. Then we reverse it. Flip it and reverse it. Oh my God. Oh, something's wrong with me. Too many lectures today. So we reverse it so that the 250 is on the left and the 150 is on the right. Okay, so the 250 is now the primary and the 100 is now the secondary. Okay, that's why I put the quotation marks. And now we're going to input 120 volts into this side. The question is, what is the voltage that comes out? Okay. So let's set up our equation. So we know that the voltage is proportional. VP over VS is equal to NP over NS. And we're using our new values, okay? And we're inputting 120. So we're going to have 120 volts over our unknown is equal to 250 over 100. Solve for VS. We get 120 times 100 over 250, which is going to give us a smaller voltage, right? And that is going to be 48 volts. So our step-up transformer became a step-down transformer by flipping the sides. And that's basically the lesson. The lesson is that a transformer is both a step up and a step down. You can just change what side your input is to turn it from a step up to a step down. So to wrap up this section and this lecture, we looked at transformers and they use a property called mutual inductance to raise and lower an AC voltage. And if there are more windings in the secondary coil than the primary coil, then it's a step up. If there is more windings in the primary coil than the secondary coil, then it's a step down. And it's opposite for current. And that's basically wraps up this chapter, or this half of the chapter. And wish you the best. Have a good one.